I think it's working. I think we just started a live stream. Yes, we did. Hello, Ben. How are you?
Great. How are you, Bill?
Oh, hanging in there. Ben and I have been talking about, he's working on his lab today, and he's also got some cool stuff to show us. Tell us, what are we going to be talking about today before we get into talking about our lab a little bit?
Well, there's a few things I thought we could discuss, but just on that subject of amazing retro rack gear, and I have a thing for old Roland stuff.
Right.
We did the SDE 2500. That's going to be an ongoing project. I just received, and you've got to love the packaging, no anti-static protection whatsoever, just shoved in some packing foam. But I did just receive these. I ordered them from a surplus electronic parts supplier, and this is an interesting thing, with the part crisis going on. You can still buy the old stuff. That's the good thing.
Right.
These are new old stock from NEC. The Quip package microcontrollers, the same one that's used in the Roland SDE 2500. It's also used in a number of Korg and Roland synthesizers as the microcontroller. The interesting thing about this, it's NEC D7810G. Well, they used to be called the Micro PD 7810G.
Right.
This is the ROM version, and back then everything was through hole. I don't know if let me switch cameras actually.
That almost focused. Try it again.
Hang on 1 second.
Yeah, now pull back just a bit. Yeah, I can see it because I know what I'm looking at. Yeah, it's a dual inline.
Crazy.
That's cool.
This is called a Quip package. So there's DIP, dual
quad
inline.
Yeah. I'm sorry. Right.
For I don't know what the Q was for. Quilted? I don't know. But basically
quad?
They have staggered pins to get 64 pins in a package that's not much bigger than a regular 32-pin EEPROM or something.
Right.
So the reason they use this is because it was one of the first microcontroller families to come with a lot of built-in peripherals, like multiple channels. I think it's got 8 channels of 8-bit A to D conversion, and some of these racks have analog potentiometer panels to control things digitally. And so they have a low-speed A to D in the microcontroller just to sample the pot voltages. And it also has a serial port built in, so they use the transmit side of the serial port to communicate to the Roland RDD control chip in a synchronous format, similar to SPI. And they use the receive part for the MIDI input for the whole unit. So the plan was for today to have originally got the SDE 2500 out and desoldered the EEPROM and read the contents of the EEPROM and start to disassemble it, but I'm not quite ready yet. I'm a bit on the back foot because I was waiting for a new desoldering gun, which only just arrived yesterday. That's in this box.
Oh, what'd you get?
It's just a cheapie I found. Just got this on Amazon. Let me switch cameras again so you can see what I'm doing. Yeah, I've got my classic plunger solder sucker.
I saw it. That's why I got mine out. Yeah, it's on your bench, so I went and grabbed my desoldering plunger.
Yeah.
Mine is 40 years old, and there's 40-year-old fluorescent orange spray paint from when I worked at Commodore, because you had to mark your equipment. So my fluorescent orange paint is still on it, and it still works. I service this. This is a wonderful desoldering tool, even 40 years later. So, but you use it in conjunction with an automated one like you're about to show us. They each have their time and place.
This is about $120 on Amazon. It was a Yihua one hung low brand, as Dave Jones would say.
Aoi is how I pronounce it.
The manual actually in this one looks it's very nicely well written and done, and spell checked and grammar checked by native English speakers. So it's got a really good user manual.
Is it a 474 by any chance?
It is. What's the part number on it? It is. It's a 2. No, wait. It doesn't have a part number. What the heck?
Somebody say the camera isn't switching, so we can't see anything you hold to the other one.
Yeah.
I don't know what that. Yeah, basically we see just your midsection right now is what they're saying, I think.
Oh, I'm sorry. I always make this mistake.
There we go. Yeah.
I forget to actually click the checkbox when previewing the other camera to make it switch. So it doesn't say what the number is, but it's
Go ahead, pull it out.
You are. This is the warranty card, I think. That doesn't say the part number either, but I'll just get it out. Oh, so I guess this is turning into an unboxing show.
Yeah, let's do it.
It's pretty well packaged.
I get asked this question a lot about what's a good desoldering tool, and especially since we've been talking about retro repairs and Commodores and stuff. And there's one of the most important things about desoldering is cleanliness, and that's what you're showing us there.
Yeah, this is replacement chamber, nozzle, vacuum nozzle, additional filters. That's critically important to be able to buy filters. I have a friend in Australia, Richard, who was one of my mentors who taught me a lot about electronics, Richard Freeman. Hopefully we'll get him as a guest one of these days.
So I have a bag of the same stuff here. You can see all my de-cleaning stuff, everything.
This is for shoving solder out of the nozzle.
Yep.
Yeah, so Richard has a Hacko, which is a name brand, and they have these little diaphragm filters. Not filters. They have these little diaphragm valves, and the diaphragm membrane is a part that wears out, and they stopped selling them through the electronics distributors in Australia. All ran out of stock, and no one had them, and they stopped making them. So that's the thing you've got to look out for. He actually asked me to find some. I found some here and shipped them over because with some of these things, they can get hard to get.
Do you mean this part right here that I'm holding up to the camera?
No, it's a little membrane that sits against that part, I believe.
All right, so it's a filter. It's not one of these filters, though.
No, it looked a bit different. It had a tiny hole in the center, and it was like a flap of flexible plastic.
Okay. Yeah, I don't have that. I have filters with holes in the center, but they're all like these disposable kinds that I'm showing here.
Oh, yeah. So this is the actual gun.
Yep.
Looks pretty good. It came with a few different nozzles. This one is, I don't know if it can focus on that.
Yeah, it is.
It's got solder in it from the factory. I guess it's... or maybe this is some kind of cap, but I think that's just solder in there it doesn't have an actual hole on it. I'll have to check that out. But I needed to get a decent desoldering gun like this if I'm gonna start taking apart 80s musical gear. I don't want to do it with this. As cool as this thing is, this actually works really, really nicely, but
it's good for a couple, but if I'm doing more than 5, I turn on my desoldering gun.
Yeah, and also I want to protect the printed circuit board. It's super easy when desoldering to
ruin something.
Eliminate the pads off the board. And
so one time in production, I was there, you know, and we were taught in production how to use the desoldering tool and everything. And son of a gun, if the manager didn't walk by while I was prying a part out. And he stopped everybody and brought him over to my desk and said, show us what you were doing again. You hear this creak noise. And he said out loud so everybody can hear, thou shalt not pry parts out of the board. You know, you desolder them to the point where they all but fall out. You know, you should be able to wiggle them out without an actual prying. Because if you're prying, especially in the old days where there were inserts for the vias, you would pry the via right out of the board if you had to pry it.
I've actually done that quite a few times in the past, and it's
they're mentioning difficult. Pace. Go ahead.
This is the other reason why I don't always want to use this solder sucker, because with a gun you're continuously applying the heat, so the solder in the pad and in the via barrel stays liquid, and therefore you should be able to suck the whole lot out.
And we should talk about how vias were made over the years at some point, because nowadays we don't do inserts, but in the old days they would actually insert a via in each hole. There was a process to do that.
It was like a little spigot, and they were super expensive.
They were, yeah. At Commodore, we literally, I don't want to say we engineered not using those, but the production engineers, they quickly changed the PC board to a plated through, which was brand new back then, it seemed like.
It's a Yihua 948. Focus, you stupid phone. Come on.
Yeah, Ben's using his phone to show us that. Yeah, I can see it pretty clear there. So you have control the temperature. Right?
Yep.
Okay.
I was umming and ahhing in my head about attempting to, on the live stream, desolder the EEPROM chip out of the SDE delay. But I'm not sure everyone wants to see me trying to desolder some chip. I don't know if that's that interesting.
We can do an insert or something maybe at some point.
Yeah. What I wanted to do is, I had planned to have that done by about Thursday night or Wednesday night this week before the show, so I could have the EEPROM out and do the reading.
Right.
But because I've been rearranging furniture and building more cabinetry for my office here, it's been kind of difficult to. So that's a nice stand. I really like the stand. It can actually, it holds it up. The stand is really good, actually. I'm impressed. This is just, without turning it on or using it yet, I can't evaluate its performance yet, but just as an unboxing so far, I'm very impressed with the build quality of this. The screws in this, the finish on the metal, it's very high quality. For 117, I think it was about $117 on Amazon. It's worth, even though this is a cheaper brand, or like not even really a known brand, it's worth having some decent soldering and desoldering gear. You kind of can't get away without having it. Just like you need power supplies, you know?
Yeah, so I did a Hackaday video on desoldering. Somebody just spurred my curiosity here in the chat channel, so I'm going to try and find. Here we go. I'll post a link to my Hackaday video on desoldering where because somebody mentioned braid, and I also have an infrared desolderer. So there's a whole art to this.
There is. I have hot air. I have braid, and now I have this. And of course, there's a reflow oven. You can, if you're really in a pinch, you can heat up the whole thing in a reflow oven, open the drawer, and get the tweezers and lift the part off the board. Right. And then there's the hot plate method, but that only works if you only have components mounted on one side. I'm just going to wet this sponge.
All right.
Quick.
So yeah, and then there's in addition to desoldering, there's also another tool that I have over here, which is actually there's handheld versions of them, but you want some way to pick up the chip flat. So we have a little suction. I'll look for it when Ben gets back. Or I have an automated one. Actually, I have one built out of an aquarium pump that builds up a suction. And the reason why it's important to pick up a chip flat is if you pick it up at an angle, you'll bend the leads if you're going to reuse the chip or whatnot. So it's good that when doing desoldering that you also have a way to pick up the chip if it's not a dipped. I'm thinking a dip chip, excuse me. I'm kind of mixing things up there too a little bit. Because we were talking hot air, so this is for through hole.
Okay, how do I get this to work?
Thermal tweeze or slick. For SMT, I wouldn't bother with those tools.
I guess.
So somebody's asking about cleaning the tip. So to clean the tip, we end up with a plunger, and you end up plunging this through the entire gun assembly to first clear that out. But then there's filters, and I've got a spare cylinder here. So there's a whole sandwich of filters and parts. And you just got to go through here, and literally every time you use your desoldering machine, I've been trained to clean it when I'm done. Because again, I came from production. If you walked away from the desoldering machine and left it dirty, they'd come get you and escort you back over. And I'm talking about the assemblers would do that, come get the engineer or technician and escort them over to the desoldering machine so that they could clean it again when they're done.
Okay. Yeah, it's not drawing, so I'm gonna have to consult the manual.
The vacuum's not working?
Yeah. Sleep mode.
So now I see you're set for 350 degrees C. I just checked mine a bit ago, and I default to 450 degrees C on my desoldering. So
wow,
that's just one of the... I'm hot and fast. Let's call it that.
Oh, yeah. It's probably better to do that than it is to go low and slow, because low and slow is going to result in via barrel damage.
Right.
Probably.
Right. So we'll have to have a show and actually use them, because there's the art to it is when you have a dip lead, you actually put the desoldering tool down over the lead and wiggle it till it's free in the barrel, and then pull the suction up out of it. And that lead should be visibly clear of solder when you're done. If it's not, you add solder and start again, is the way I've been trained.
So I didn't realize it was flashing. It still wasn't quite up to temperature.
Oh,
and
okay.
Then you heard those 3 beeps. You heard the 3 beeps.
Okay.
That means, okay, I'm ready for business now.
Oh, wow.
So
Very cool.
I don't know. I'll grab some random board and give it a try. Well, that's
Yes. Yeah, somebody's talking about how quickly they clog up. So the other thing, Ben's got a glass tube. You can see it on his. Hang on. Let me change my viewpoint here. Yeah, there's his glass tube. Eventually, I used to have glass tubes, and now in my replacement kits, they've been giving me something that looks almost like it's not carbon fiber, and it shows the direction it goes and everything. And this is where the hot solder ends up going.
Bill, why do they have a big spring inside the tube?
It catches the solder. And I've had those tubes so clogged. Here's my spare. You're talking about this thing here.
Yeah. Like, how does that work?
That's where the solder actually lands, the big blobs of it. And so this will get so clogged, air can't get through it, and you have to plunge this out separate when you disassemble it. So this is the real filter as far as I'm concerned. The small membrane filters and stuff you're talking about, that just keeps small particles out of your vacuum pump. This is what actually catches the solder.
You know, it's really satisfying looking at the top side of the board and seeing the solder get sucked down through the hole and away.
Isn't that a cool thing? This
works so nicely. Let's see if I can get a close-up. So I can pretty much
wiggle it out.
Wiggle that a little bit, and it just comes right out super clean.
Wow, that's cool, isn't it?
So It's always a good day when you get a new tool. Come on, new tool day.
We should do that.
Day.
Yeah. Yeah.
That makes
So
me
yeah, to the people at home, if you do find that it's daunting to try and remove stuff yourself, having the right tool helps a lot. And so again, I've been trained to use a desoldering tool since I was a young technician.
And they've never been more accessible or affordable.
Oh, ain't that the truth? In the old days, a pace cost a couple $1,000, $3,000 or $4,000, and that's back when I made $24,000 a year. You know, so it would have been a significant part of my income to get one. Now they're $100 some dollars, as you were saying.
Yep.
Yeah, somebody mentioned you can apply flux. Absolutely, flux helps. I keep a bottle of flux. Matter of fact, let me grab mine. Unless I moved it. Yeah, I already have it over here. Hey, how about that? Yeah, I keep a bottle of flux. I use the no clean flux. I flood the board with this stuff. You just can't have enough flux, in my opinion. So get the flux out of here.
Especially any SMT, and also cleanup. I mean, cleanup afterwards. No clean. Technically, you can just leave the residue on the board and it won't harm it. I still like to clean them.
Sure.
You know what's real interesting? So this week is IPC Apex Expo in San Diego, here where I live, and I'll be doing an RF and microwave PCB design class there on Monday. But the trade show itself is immense. They have full assembly lines. So basically, it's the electronics manufacturing industry show. So all the companies that make the pick and place machines, the soldering ovens, the washing things. And the cool thing is that they set it all up there in the convention center, and you can go watch it all in action. There'll be some actually assembling and soldering boards together, like just little test boards. And cleaning is really interesting, because you would think they'd use some sort of very special, expensive chemical, and some machines and plants use some chemicals to do washing. If you're doing cleanup after desoldering or rework, you want to use a toothbrush, mark it so you don't accidentally put it in your mouth again afterwards. Use a toothbrush with some isopropyl alcohol, which is just rubbing alcohol. You buy it at the pharmacy. It's cheap and plentiful. Isopropyl alcohol and a toothbrush does a marvelous job getting rid of the flux. But in the factories, they just use purified water. And
we had a dishwasher. Yeah.
Yeah, it's effectively a massive dishwasher, and they hang all the boards in it and just run them through a cycle. And it cleans everything, and then they dry them out and then ship them to you.
Right. So in the late 70s, we got a dishwasher for through-hole boards at Pennsylvania scale company I worked at, but they weren't using deionized water, so we were getting water stains, quite simply. And one of the things they looked at was Cascade, and the reality was they put in a water deionizer to clean the water. And we had to use water-soluble fluxes. You know, you don't just use water without being part of a flux system.
Yeah.
Right?
Yeah.
So you mentioned cleaning boards. So there's the isopropyl alcohol you mentioned. And I also keep like 99%, 98%, something like that around, so I don't get stains and stuff. But also, then they do make flux removers for PC boards. And as you said, you use your toothbrush in a well-ventilated area to scrub your boards clean. And these are, again, part of a system. Depends what you're doing. I use this stuff on old equipment I didn't make myself. You know, it's got old, cruddy flux on it.
Yeah. Yeah. Well, that was cool.
Yeah, you want to talk about Roland now?
Oh, yeah. Yeah. So I have this. Let's show the rack, right? You can see I'm still getting organized on the studio side. I don't know if you can read any of that, but one of the things there is a Roland GP8 guitar effects processor. The GP8 was kind of groundbreaking multi-effects unit. in the mid 80s. It was the one everyone wanted, and it was confusing. The messaging was confusing because people thought it was in a rack and it was MIDI programmable, that the whole thing must have been DSP, but it isn't. The interesting thing about it is it's actually exactly the same as all the most popular Boss guitar pedals, because Boss was a sub-brand, or it's a brand of Roland, right? So
okay,
every guitarist knows and has at least one Boss pedal, right? Or has owned some in the past. They're classic, and they've made millions, literally hundreds of millions of different pedals have been made. Like the Boss DS1 Overdrive, they've probably made 8 million of those, or 10 million of those. So
okay,
the thing is, back then, it was too expensive. Like the only DSPs available were like the TMS 320 series. They were very expensive.
Right, from TI, yeah.
They were 16-bit, and they weren't quite fast enough to do real-time audio beyond. They were mainly employed as codecs for telecommunications and things like that.
Right.
They weren't particularly good enough for delay. This is why when we looked at the SDE 3000 and other old Roland delay units and reverbs, they had to make their own custom ASICs to do the DSP. And those were much simpler than what they would be today. So I'll just turn this off and move this over. So one of the cool things was I got a Roland GP8 given to me by a friend in the 90s, and I wasn't using it because I had a whole lot of other gear. I had a Marshall JMP1 preamp. So that was a valve preamp, a tube preamp in a rack that was MIDI programmable. That was the best thing ever. Sorry about the noise. There's construction going on in the office next door. Someone's gutting it. I don't know if you can hear that.
Yeah, a little bit, but it's not a problem.
I hope they leave the insulation in the wall. They better damn well do that, because I need soundproofing. Anyway,
we could do a whole show about soundproofing too.
Oh yeah. So my friend, who was a bass player, he had this GP8. He'd lent it to someone, and they fried it, because being the ignoramus that they were, whoever they were morons. They're like, how do we use this thing? I know. Let's plug the outputs into the mixing console, and we'll plug the inputs into the output of the guitar amp.
Oh yeah, that'll ruin it. Whoops, lost you there too. What Ben was talking about there you are. You're back. So we heard you say they plug the inputs into the outputs.
They plug the inputs of a GP8 into the outputs of a guitar amp. Not the effects end.
Right, which is completely different than the 1 volt peak to peak signal we typically use for audio.
Yeah, so the whole input board was completely fried. So this guy said, "Oh, it doesn't work. If you fix it, you can have it if you want to try and fix it." I'm like, cool. So I went down to Roland headquarters in Australia, which was in Sydney, near where I lived at the time. I said, "Hey, can I buy the factory service manual for the GP8?" And they sold it to me. Now these days, I asked them recently for the SDE 2500, and their initial response was, "No, you're not an authorized repair center, so we can't sell you." So they changed their policy, but these old units, most of them are available online. You can find these service notes, on manuals and other websites. But I have the original factory printed one, and it is a beautiful document. So I'll just switch cameras again so you can see it maybe more clearly.
Right.
These people, the way they document their products, just amazing. So the front has all the specs, and we're looking at the affected frequency response peaks out at only 12 kilohertz, but that's okay. A guitar amp system doesn't put out much more than 4.5, 5 kilohertz. except for some tangy detail. So that's not a problem. It's the same Roland digital delay chip that we looked at last time with the 12-bit quantization. Only in this unit, they don't do the companding that we looked at. They keep it exactly the same as the original Boss DD2 pedal. That guitar pedal, the Boss DD2 just limits the use of the chip to 12 bits only. It doesn't have the companding RAM. It does have some companding in analog though, with an NE570 chip. So everything's there, and all the pages fold out. All their manuals are dual language, Japanese and English, because of course it's a Japanese company. Oh, I love this. Look at the pages. The pages look yellow, and you think it's because it's old, but they were actually, this is the original color of the factory paper they printed on, was this slightly yellow color. So even the pages are kind of nice.
Right.
But the full-on exploded view diagram there of all the chassis and everything. I don't know if I'm showing that the right way. That's probably better, isn't it? So you see every nut, every bolt, every screw, every piece of metal, every bracket, every heat sink, every board, every switch cap and cover, and the LCD panel. And I'm thinking this is a standard, these LCDs, this is one of the first units they went to a character LCD. The previous units that we've looked at were vacuum fluorescent displays that were numerical only. Okay. I'm considering changing this one up. If I do some mods on the unit, I'll change the display up and make it a blue one or something. They've got, what I loved about this too, like they made everything to be serviceable. They really were thorough. They give us the whole bill of materials for the whole thing. Right. So here we have all the panels, all the part numbers from Roland. If you need to replace the display panel, you can get it. This is interesting. It says DEP5 sleeve. Now I have a DEP5, Digital Effects Processor number 5. It's like they're reusing some parts in multiple different units, which makes sense. All the different jacks, the actual replacement boards, and then they start with the electronic components. So they list out every Roland part number and the manufacturer part number with it. So there's power transistors here used in the voltage regulator section. And so every part you can get. They've got the delay gate array. They had a chorus gate array from a Boss chorus pedal. A system gate array. And that's interesting, this MB62H195 system gate array, we'll look at that in the circuit diagram because it plays an interesting role in this device. So we have digital chorus and digital delay, but the interesting thing, all the other parts in here are, there's our 4066 quad bilateral switch. Right. There's analog companders, NE572 programmable analog compander. There's voltage regulators, there's op amps, and some glue logic stuff. But pretty much everything else, they have two interesting Opto isolators here as well, a PC910 and this other weird one, the P1501, which plays an interesting role in this circuit. Then what they do, they give you the pinouts of every chip used in the design. And a description. So look at this again, the P1501 Opto isolator right here. I don't know if that's focused enough or not, but you see that's an interesting... We see that, yeah. The receiving component is not a transistor. It is not a gate. It is a CDS cell. Cadmium disulfide. Cadmium sulfide. Yep. So it's a resistor. Optically controlled variable resistor. So this part can be used for things like optical compressors and other purposes. And so what we're really looking at here is a unit that was an early multi-effects unit, and this is what I love too. The op amps they used to make them compact in those Roland and Boss gear from the 80s. They had dual op amps everywhere, but they used them in SIP packages. Which are long and thin, stand up straight on the board like a billboard. And so they take up hardly any room. And if you use SIP package op amps with resistors mounted in a U arch, you know, so they take up less footprint space. That's the only way they were able to make these early effects units and guitar pedals fit in the tiny little boxes that they made them fit into. So it's really interesting to see. Just as like this is the first era of mid 80s surface mount technology. There were only 2 or maybe 3 surface mount parts. This one, the CPU in this one is the 63 Hitachi HD6303 RF. We could look at that too, because I've actually found I found the mother load. I found the whole Hitachi data book for the entire family of these things. It's like 700 pages. But everything is just so nicely laid out. Then they give us a block diagram, right? Here's a block diagram of the system. So there's different boards in the thick outlines. You still hearing me, Bill?
Yep, I'm here. I was looking for my Hitachi manual, but couldn't find it. My data book.
So this is really interesting. Look at this. On the top of the block diagram, we have all these blocks. We have dynamic filter. That's like a auto wah or controllable wah.
Okay.
Compressor. Overdrive. Distortion. Phaser. Equalizer. It's just a 3-band EQ. Digital delay. Digital chorus. And master volume. And so what you see from looking at this, these signals coming down from the main control board, these are all signals like Q, sense, up, down, center frequency, filter on, filter off, sustain, attack.
Are those analog signals?
They're all analog control voltages. And these effects, which are in a fixed order, which is the sensible order that a normal educated guitarist would have on their pedal board, each one of these is essentially a Boss pedal that you could have bought off the shelf. And instead of having knobs on them, they've put them all on one circuit board together.
Right.
And they've found a way to replace the knobs with FETs and other variable resistance parts that can be controlled with control voltages. All those control voltages come from, there's effect on-off interface.
Right.
We'll look at that. That's an interesting circuit, how that works, that they had to do some fairly big level shifting to go from logic to plus or minus 15 volt control swings.
Right.
Which is shown, it's notated here on the diagram. And then, so we have our main CPU, we have our system gate array, the EEPROM, and control signals coming out from the system gate array and the CPU to address decode, to control latches for all the effects on off and the LED display, and control to the chorus and control to the digital gate array. And everything else that comes out of here is, they say this NJU7302 times 3 and some D to A converter.
Right.
So what this is they have a D to A converter and some sample and hold circuitry and analog mux that keeps all the different control voltages coming out to all these different signals.
Right. Holds them.
So yeah, it holds them steady. And amazingly, the whole unit has very low noise.
Right.
It's noisier than a unit would be today that does everything digitally, but the benefit of it is like guitar want the original analog overdrives and wire things, and would prefer to get a guitar pedal. Well, it's all included in this, and this is how this one worked. And so it's like, so you can see, like there's the control voltage table. It shows for all the different parameters what the checkpoint is. IC1 pin 14, 15, 13, 12. IC2 pin 15, 16. So these are the checkpoints to check the different control voltages at different control values in the software. So if I set the auto wire sense to 10, its voltage should be down near 0 when I put my crow probe on pin 14 of IC1, and so on. So all these analog CVs come out of these. These are like analog, I guess they're analog mux chips. These NJU 7302s, they have 3 bits of control input, then they have an input voltage and an inhibit, and then 8 outputs. So they demux the voltages on the control output DAC, which is just an R2R ladder coming from the system gate array through a buffer, and then those get demuxed. And then each one, I'd say each one has a capacitor on the output as well to hold the voltage more or less steady. So the manual has all these sequences to go through, like flow charts, how to set up to do testing and measurement in the unit. I've never bothered to do that because I never needed to. The one that I was given in the 90s, I repaired. I could totally see where the problem was. It was, you know, the input board had all these fried resistors and op amp chips that were burnt out right on the very input. So I just replaced all those and it worked.
Wow. Okay.
But
I love the art of folding that they used to do in the old days to make this stuff fit in manuals.
Just amazing. Like, look at this delay bias setting. There's a knob, there's a pot on the motherboard to set the bias on the delay input A to D such that you get maximum dynamic range instead of you start to clip when it's offset.
Yeah, look at that.
That's
pretty cool.
Distortion offset. You want some offset in a distortion or overdrive because that mimics an actual tube amp. So analog overdrive and distortion pedals almost always have some kind of, there's different sounds, right? There's one that sounds very harsh, and that's a regular back-to-back diode clipping. But the more common smooth overdrive tone is with an offset high gain FET stage or transistor amp stage that's got some bias. So when it clips asymmetrically like a tube amp would, and it gives you that same nice even harmonic distortion that guitarists love. So yeah, everything's just so nicely laid out. I'll keep that folded out actually, because this is our main system circuit diagram. And you can see there's also a preview of the board, which is colored, so I can tell what's top layer copper, what's bottom layer copper. So anyway, we'll look at that in a sec. You see the Boss brand name is there, even though it's a Roland branded product. Which is, again, it's all the same company, but it was probably the Boss team that did the design on this hardware. So, this one is getting kind of tricky, and I don't want to damage my original service manual here. So
yeah, isn't that amazing when the service manual has value also? Not just the equipment, but the service manual is retro.
So here's the main board. So this is the main digital stuff. So again, like last time with the SDE 2500, we've got our delay gate array. It's the exact same chip, the one that I intend to build a replacement for with FPGA.
Okay.
And one of our Discord members basically just went inspired by our last stream about this and just did it overnight. Built one in Verilog.
Oh, no kidding.
Yeah.
Did they talk about that in our Discord?
Yeah. It was in the chat channel.
In chat channel. So
Yeah.
just so everybody knows, I posted a link to our Discord channel at the beginning of the chat here. And as Ben just mentioned, we talk about this stuff all week long. And you want to meet somebody that just did an FPGA of something we talked about a couple weeks ago? Join our Discord.
Yep.
So
the main
all right.
main controller here is this. I mentioned the HD6303. This is a big daddy one. This is I think a 64 pin version. Actually, no. This is one of the earliest surface mount microcontrollers. So it's in a rectangular shaped package that we saw before. But the 6300 series was Hitachi's second sourcing of the 6800s from Motorola. So it's the same architecture and the same instruction set, plus maybe some extra instructions and some microcontroller peculiarities. Like I think this one also supports some bit addressing modes and things like that, which you want. I was worried I wouldn't be able to do any reverse engineering on this, because although it has an EEPROM, all of the address and data lines go through the system gate array. But then I realized when reading more of the manual again on this system gate array, based on the PCB, included the address latch inside the system gate array. So the system gate array essentially does some of the control voltage. It does the key scanning, it does the display output, it does memory mapping for the whole system, and it does the A to D for the control voltages for all the effects. And so it has some registers and things inside it for all of that. And it also has the address latch. So with some of these microcontrollers, as people would know, they have multiplexed address and data lines. So in a program fetch, there's an address latch signal goes high, and that puts the upper 8 bits of the address in the latch, and then that goes low, and then it uses those, or maybe it's the lower 8 bits, I forget. But then that part of the bus switches from being address to being data bus, and it reads the instructions and data out of ROM or to and from RAM. So I'm not sure how the whole addressing map is what the address map is in this hardware, but it's doing something there with it.
Right.
So and then there's a MIDI I/O interface down here. So that's the serial port of the microcontrollers, almost always devoted to MIDI in these situations. And then
all this takes me back to the fact that I learned electronics by reading manuals in the early days, and I'm talking the early 70s. You can actually learn because they're showing you all these waveforms, and they're showing you how things turn into other things. You could actually learn a lot about electronics from these manuals themselves.
That's right. The manuals basically teach you how the thing works so that you can fix it.
Right. Yeah, I learned to fix things before I learned to design them.
This is the effects on-off controls, and you'll see they have these dual op amps, and they're all set up with there's 754 HC754 latches. So the processor just sets or clears bits in these latches to enable or disable an effect in the effects chain. But because that's 0 to 5 volts output, they need to level shift it to control the FETs, which switch the effects units. Each individual effect has its own FET switching using JFETs. Now to turn a JFET on and make it go from being an open to a short, you have to pull the gate, FET source drain gate.
Right.
You have to pull the gate down to a negative voltage because they're depletion mode device JFETs. So you have to pull the gate down to some negative voltage to get the channel to go to a very low resistance and effectively turn the switch on. And so that's what they're using. They're actually using op amps as comparators to do level shifting. So if a logic 1 comes in here, and they're doubling some of these up, but look at this, FT on at the bottom.
Right.
FT on goes to one of these op amps, right? Through a 1 megohm. They have a 1 megohm output impedance. They're kind of a weird op amp, these.
Right.
It's actually they're drawing that in a box, but really what they're showing is
there's 4 of them there.
Circuit.
Yeah.
This is a repeated circuit, and this was actually a feature of hierarchical schematic design tools. Altium does this too. You can actually draw a sub-circuit and say repeat. You can put a repeat command, and it'll make it look like there's a stack of them there, and you can have a multi-channel design. So I guess that's how they did this here too. But they have a 1 megohm output impedance in series with the op amp. I guess that's to help protect the FET from and also reduce switching clicks, because you don't want a sudden heavy current going into the
right. It's obviously a voltage device, and the proof is it's such a high value resistor as opposed to a current device.
Yeah, and then they have this stabilized voltage divider from plus 5 volts to ground. They've got a voltage divider, just 10K, and some capacitance to make it quiet.
Right.
And the inverting input of every op amp is just hooked up to that. So that's half the VCC for the digital. So when a logic low comes, the op amp just switches hard off. When a logic 1 comes, the op amp switches hard on. And when it's hard on, the output is, because the op amp's powered from plus and minus 15 volts, the output goes up towards 15 volts. And
now, what year was this made?
Off. This, I would say this was designed, this must have been designed in, I think, 1984 or 85. Okay. Maybe it may have been later. It may be in 86, but these GP8s were, I remember being in the 7th grade when these were released. So that was 1987. So yeah, this was probably designed in 85, 86, and then released to the market in full force.
And that's my memory of like the 16-bit families came around that time. Early 80s, we were still pretty much in 8-bit land.
Yeah.
But it's still a hybrid of analog and digital to pull all this off, which is why we love retro gear here.
Yeah, check out this PCB layout. What I'll do, I'm going to actually pull my phone off the stand, and so this can lay flat, and it's more well lit. So forgive me if it's jerking around a bit. So this is the main circuit board. It's pretty big. This is about a 1-to-1 drawing.
Two-layer board. You try and hold it still. It's tiling as it moves around.
It's 2 layers.
There you go. Yeah.
The surface mount chips are, I believe the orange traces are the bottom layer and the gray is the top layer. And the surface mount chips are mounted on the bottom of the board, because the whole thing, back then everything was wave soldered. So
drag or wave soldered, yeah.
Glued these surface mount chips using glue dots first, and then placed everything else from Juki placement machines that do through-hole insertion automation, the pick and place for through-hole parts, basically. And
auto insertion,
would have gone through, the whole thing would have gone through a wave soldering machine. So the whole bottom of the board was passed through a wave of solder.
Right. Which is amazing to think that chip had itself then get submerged in solder, but it's for a short period of time, and it's designed to do that, to be submerged like that.
Right, and the other telltale that it's wave soldered, I don't know if you can see this, the pads on the corners.
Right.
They're all extra wide, and the reason is from the wave direction that it's soldered in. This one could be soldered in any direction, and these will collect the backside of the wave so that no bridges form.
Right, right. So we used to have a drag solder machine at one place I worked at, and where it actually would sit down into the solder. It would come over, it'd get preheated, and then drop into the solder flat and then come back up out of it. Wave solder is there's actually a fountain of solder, and the board just progresses through it. And as Ben just mentioned, there's a direction component to it. So part of the art of mass production is understanding your solder process.
It's really, really important. Really important to get good yields and not have failures in production.
Right.
So we can see all this half here, all of this. It's all analog, all of it. This is all through-hole components.
And this is back when we did mass production in Japan. Japan was known for being able to do this density. It was the era of the transistor radio, and it was before China was open. So now, just as we do our production in China, we were doing all our production in Japan back then.
Yep.
Not all our production, but a good portion of it.
Which are those analog muxes.
Right. Right.
They'll take a series of analog waveforms from probably this resistor here is the Dac output from the system gate array, which is this part here.
Right.
Right. So the Dac output is here. It's muxed out to all of these to a bank of capacitors which hold the voltages steady after the demuxing of the analog control voltages. They're all stored in these caps. And then that goes on here, and this river of routing here on the top is the analog control voltage signals that go all throughout all the different parts of the circuit.
Right, right. That's cool.
Here we have NE572. That's a compander for there's another one there. These are the companders that give us the decent dynamic range for the 12-bit digital delay circuit. Another compander, and all op amp filters for pre-emphasis and de-emphasis and anti-aliasing.
Right.
This was all done with solid state and discrete parts.
Right. And we spoke about in our last show that we talked about the Roland. We talked about companding and just what it was, and a little bit about Nyquist and some of the filtering characteristics.
Yep. So if you haven't seen it, go back and watch that episode. It's really cool because I actually probe some of the signals in the SDE, and we look at it on a scope.
Maybe we can get you to do that for our next Roland show. Actually, get some scopes on here and see these analog control voltages. Yeah,
totally. Let's do it.
That'd be cool.
So this is the Roland digital delay control chip. This is the classic big chip that's in the DD2 pedal. The original DD2. The replacements, of course, since then don't use this. The SDE 3000, the SDE 1000, and 2500 that we looked at last time all use this chip with SD-RAM 4164s. With 6 4164s, and at the sample rate this is sampling at, this unit will give a maximum of 1 second of audio delay time.
Wow.
And it's just a simple 12-bit R2R resistor pack goes on this side of the chip here, and that's the DAC, and also the DAC for the sample and the successive approximation sampling that this chip uses with an LM311 comparator and a 4066. Yeah. There's the 4066 for the sample.
There it is again. Yeah.
And our sample and hold caps, and this IC here. I don't know, I can't tell which one that is.
And there's a whole conversation we could have about droop compensation for sample and hold circuits, because sample and hold circuits aren't perfect. So you sample something and then it starts to decay, And so one thing you can do is inject an equivalent amount of current back into it, or refresh it more often or whatnot. But there's, yeah.
And in this case, they keep it simple. They just use a source follower op amp. And so this is a dual op amp chip here in a package that does the sample and hold for the input and hold for the output of, and one of the op amps is a gain of one source follower, and another one for the input side.
Right.
So over here we have all the 574s. So these 8-bit latches latch in the on-off controls. So up here we've got the analog control voltages. Down here we have these registers, 8-bit registers, which are driving those dual op amps with the 1 mega ohm output, and all of those signals go off into this river on the orange layer, which I think is the bottom layer. And they go off all around to all the different JFETs around each of the different effects circuit sections to switch them in of the loop or switch them out.
Wow, amazing stuff for the day. It's just
incredible.
Nowadays we'd integrate the heck out of it.
Yeah, there's literally, I don't know, probably a few thousand parts in this.
Right. And what was the signal to noise ratio? Do you remember on these things? They were quiet enough to be on stage, right?
They were quiet
with lots of amplification.
Yeah, they were used in studios, so they were pretty good. The specs for that might be here somewhere. There's the MIDI. There's all the MIDI system exclusive and MIDI implementation chart. Yeah, I don't know. Maybe it's in one of the earlier pages.
Yeah, well, we'll find it during the week or something, but...
It's here on the front page, I think.
You got your compression levels, your delay time. There's that 1 second delay time. Cool.
Yep. Frequency response for the digital delay.
Right.
Digital chorus has frequency response. The chorus has slightly higher frequency response. It's because it's using a higher sampling rate, and that comes down back to that Nyquist thing. The chorus samples at 50 kHz.
So somebody asked what kind of filters that are used in here. Any guess as to the organization of the Nyquist filters as far as?
Well, let's look at the analog part. So we haven't looked at the analog piece circuit diagram yet.
By the way, we're at an hour now, just so you know.
Okay, so it's really clearly laid out. Again, it's a bunch of Boss pedals, but put into one box. So they start with the dynamic filter. So you want to talk about filters. This is the one that does wah, auto wah, and it can be controlled by MIDI. The MIDI foot controller that came with the GP8 was called a FC100, and it had a pedal on one side. It was the first of its kind. They're very common now to have guitar stuff that has pedals plug in. But it would send over MIDI a control voltage value, which could be 0 through 127, and then use standard MIDI CC commands. From that, the CPU would actually change the control voltages, and you could assign it to any parameter. So here you would assign it to the center frequency, and that would sweep your wah.
Okay.
So you could have a wah-wah.
Right.
So this one is using, what's the part?
And a wah-wah is exactly that. It's a sweeping filter, correct?
Yeah, I think it's this M, it's a Mitsubishi part, the M5207 is some kind of voltage controlled filter chip. Oh yeah, and they use NEC 4570 op amps everywhere, which are at the time they're bipolar op amps, and they're extremely low noise, even by today's standards. These op amps have 1 nanovolt per square root hertz input noise figure.
Right. I just looked up the M5207, and it's a low noise voltage controlled amplifier. So that would work in conjunction with the filter.
That's a VCA, and the other one here is the M5241L.
All right, let me look that up.
So the VCA is actually the center frequency control is coming into a kind of op amp buffer and clipping circuit. It gives it some maximum and minimum limits in analog land.
Right.
And that is being driven into pin 3 of that VCA. So the VCA, like a lot of analog signal processing, can be done with state variable, what's called a state variable circuit. It's basically, you can get an amplifier and with capacitor in a feedback loop, you're configuring it as an integrator. And this is also how PID controllers used to work in analog times, controlling motor speed and things like that. But essentially, you've created a servo, and with different combinations of amplifiers configured as integrators with feedback, and by varying the values of feedback or amounts of feedback, you're creating filters that can be either low pass, high pass, or band pass, and you can vary the frequency cutoff or center frequency, right. And you can vary the amount of amplitude, boost or cut. And this is also how parametric audio EQs work. A parametric EQ is a state variable filter using 3 integrators and 3 different feedback loops, and you're just varying the amounts of feedback in the different three groups. And there's a whole, anyone who's studied a Bachelor of Engineering would have ground through a class called linear systems, where all of this stuff, the theory of it and the math behind it is discussed. But
well, I was going to say the art of this is getting a linear response to a linear control voltage as well.
Yeah.
Over its operating range. Yeah.
Yep. So did you find the?
I did. It's a dual VCA also.
Right. So by using VCAs and op amps, see that right there. That's an op amp with.
That's an integrator capacitor. Right there.
That's an integrator, and that's another integrator. So by putting 2 integrators with variable gain that you can control remotely by a CV, you've created a state variable filter, and you can. This is essentially a single band parametric EQ, but they've configured it such that it's used to the guitarist's ears. It's a wah-wah pedal.
Right. Very cool.
And these are the switching FETs. Boss pedals always used FET-based switching, which is very low noise, and I actually prefer it. Some guitarists prefer true bypass, saying, "Oh, well, the FET switching affects your tone." I guess in some cheaper pedals it does, but the way Boss did it, they were very careful not to harm the guitar tone. So in my opinion, if you were to do a double-blind A/B test, very few guitarists would hear any difference between true bypass or FET, except that the true bypass will always click when you hit the...
Well, I was going to say, we had something called thump, right, where the control voltage would get into the actual signal. So again, part of the art was how to keep your thump out of your signal path.
Right. And that, as always too, they use this extremely low noise op amp, the 4570s, again.
Right.
With no gain, you get essentially no frequency spread noise on that. That's a source follower.
Right.
A voltage follower is the proper name, and when it's an op amp, because the source follower is just a single FET buffer, but they buffer the output. So they're either switching bypass or switching in. So there's two plus minus 15 volt on-offs for turning off and turning on.
Right.
Then it goes to the next. So the filter output goes through just daisy chains.
And back then, it was real common to have plus or minus 15 volt supplies in addition to plus 5, if not minus 5 also. I just grew up on multiple voltages. These days you can get away with 5 volt supplies doing a lot of analog-ish things. But back then we needed the headroom of the supplies.
Yep, and high-end audio gear even today still runs off plus minus 15 or even plus minus 16 if you're talking microphone preamps, because you want higher voltage supplies, so you have way more headroom before you run into clipping.
Right,
and noise issues. So the compressor uses the same VCA, but this time not configured as a filter, but configured as a compressor. So this will do dynamic range compression, and this is like a Boss CS2 pedal, which was a blue colored pedal that bass players love. Every bass player I've ever talked about said, "Oh, the Boss CS2 is the best compressor." That comes around to the turbo overdrive. This is my favorite part of the circuit, and this is one of the best sounding overdrives that's done in solid state in a guitar pedal I've ever heard. The Boss turbo overdrive is in the Roland GP8. It's exactly the same. You can compare the circuits and you'll see that they are the same thing.
Right.
Exactly the same. The only difference is, instead of potentiometers for the gain, there's two different overdrive circuits in the turbo overdrive. There's the lower gain setting, which just starts to break up and is bluesy, and it can make any tube amp sound wonderful if you put this in front of a tube amp. It's just it is a magical sound, right? So this is like the original Boss, similar to the original Boss SD1. It's got a different character than an Ibanez Tube Screamer, which is the other famous one from the era, and they're both good for different sounds.
Right.
But this is just a beautiful bluesy drive that can tip any moderate gain tube amp into face melting amazingness. And
I love how many FETs are used versus transistors in the old audio gear.
Well, and that's it. Like, Toshiba stopped making all these FETs. These are 2SK184s, which are very, very low noise. And the reason you use a FET is you get a very high gain input. Very high impedance input. Right. Almost as high as a MOSFET.
And there's your Opto isolator right there,
and
to your right.
The magic. The Opto isolators with the CDS cells, there's two of them, were used for the gain control. And so that the CPU sends an analog control voltage to a very interesting op amp circuit that drives the LED. You can see it's driving the LED. And there's an adjustment too, so you can actually adjust the gain range for the turbo and for the main channel. So there's a main channel, and there's a turbo channel, which is a lot simpler, but much higher gain. Now look at this. So they're driving an LED through a 470 ohm resistor from an op amp.
From an op amp, yeah.
Yeah, but from its input, not just the output to ground. It's when this control voltage, the drive control voltage. Now let's think about this. It's going into the inverting input of the op amp, and that makes sense because the LED is facing into that. So as this voltage goes high through this 4K7 resistor here, and is biased as well by this pot, which you can adjust, this LED is actually sourcing current out of the inverting input.
It's input. Yeah, I'm looking it up right now to see if it's like a Norton amplifier or something.
This is a virtual ground. This is just a regular low noise op amp, the 4570.
Okay, so it's not got like a current mirror input or anything. Nope, I'm looking at the schematic of it now. Yeah.
But there's enough, because it's a bipolar op amp, there's enough current can come out of the input pins of this op amp, because it's fed from an internal current source for biasing. Enough current can actually come out of that it can drive an LED. So remember, op amps, the inputs are at a kind of virtual ground. The op amp does whatever it can to keep the inputs both
equal to each other. Yep.
And the non-inverting input's tied to ground, so it tries to drive whatever current it needs to on its output to keep the inverting input also at ground. I'm marking my schematic there. And so what it's doing is it drives pin 8 low towards the negative 15 volt supply rail to source current through the LED and the other one's there just for some rectification.
Right.
And
Right.
protection.
Keeps them from saturating in the other direction, possibly.
If this voltage goes high, it puts current into the inverting input, and the op amp output goes low to compensate and pulls that current through the LED, and it begins to turn on. And LEDs have a very non-linear.
Right. I was going to say non-linear component. Yeah.
They're very non-linear. They turn on quite suddenly, which is why we use PWM to control them normally instead of an analog voltage. But the brightness of that goes accordingly to the input voltage, and that gives us the variable resistance here for the gain. And they're using Zener diodes end to end to do the hard clipping on the turbo stage. So there's a pretty high voltage. There's a pretty high voltage signal appears here because this is a very high gain circuit powered from plus and minus 15 volts. So the output here is quite a high voltage. So we have
they're clipping it at like 4.7 volts. It looks like.
Yes.
Yeah.
Yeah.
So that is a pretty high voltage for an analog signal.
And for a very, very high gain distortion or very high gain overdrive sound, to get the level of overdrive, that means the signal here at this output is already a very, very much a high voltage compared to a regular guitar level. It's higher than line level. And the reason for that is that's how you get low noise. You get the distortion, but you get a low noise floor, better dynamic range.
Right.
We use, and this is essentially a discrete op amp. This is a classic Boss discrete op amp. You have an inverting input, you have a non-inverting input, an inverting input. This is a long tail pair, just biased through resistors. The output of this FET is inverted with respect to the input, so it drives a PNP. This is a very high gain transistor right here, and there's no local feedback, there's no emitter resistor. So essentially, this drives the bass, and this is output buffer and voltage amplifier stage of this op amp. And then there's the feedback back to the inverting input.
Right.
And in the feedback loop, we increase the gain, we do some frequency compensation, and we do clipping. And so that's the Boss Turbo Overdrive, but digitally controlled using a very clever little Opto isolator circuit. I love it. This is cool stuff.
Right. Wow. And we're at 20 minutes after the hour here. How much more analog is there? Oh, there's one.
There's a lot. We can come back to this another time when I'll put it on the pitch and we can look at
this be a great segue for putting it on the oscilloscope. Yeah.
So yeah, I know we're 20 over, so I'm gonna
Whoop, you're breaking up. There you are.
Is that better?
Yep, you're good.
Yeah. I hope everyone likes it. I haven't been keeping an eye on Discord or YouTube this whole time. Have you?
Yeah,
I've got no idea if this is actually
I've been answering comments and stuff, but yeah, people have been following along.
Yeah, so we'll come back. So come back again next time, and
Ben will play a guitar into a guitar into it. See, I'd love to see live signals. I'd love to see the compander working, right? With you playing, giving it a guitar stimulus. That'd be excellent.
Yeah.
So now, real quick, when did you get this manual? How long ago?
I bought it from Roland Corporation in Australia in Actually, it was much later. It was year 2000 because I was just newly married, and that was the year 2000.
Okay.
Or 2001. Yeah, I had this unit kicking around, and I'd been meaning to fix it. It was just sitting in my parents' basement. I'm like, you know what, I want to fix that thing. So I went and got the manual.
So I'll go ahead and plug it and say, and if anybody's got some old audio gear and you don't know what to do with it, send it to Ben. Talk to us on Discord. We'll get you an address.
And if
possibly,
if you
go
want
ahead.
something fixed,
I was going to hang you out there like that and say possibly fix it for you. I didn't want to sign a check for you, but
yeah, I mean, if you don't care, if you have something old, like again, this one came to me because it was broken and the guy didn't know what to do with it. It was old. At the time, it was all 10 years at least.
yeah, you're breaking up.
And now this is what's called a sleeper effect to you. Just not me.
We lost almost everything you said. Try and repeat that once real quick.
Are we back, Bill?
You are back. Yes.
Oh, yeah. This is what I call a sleeper. You know, when something is easy to get and low cost because people don't understand its value, it's called a sleeper. Like a car that's been hot rodded but just looks like your grandma's sedan, right?
Right.
This is what I call, the Roland GP8 is what I call a sleeper. You can still buy at Guitar Center each of the effects pedals that are in this thing, and they will cost you collectively probably about $2,000.
Okay.
You can buy one of these GP8s on eBay or Music Go Round, or if you don't mind paying $20 or $30 more, Reverb, for I want to say under $150 if you're patient.
Yeah, yeah.
So you get, and they're the exact same circuits, so they sound the same. They're the same quality. The benefit is you get them all in one box, and all you need to do is control them, and you get programmability with it. So it's a sleeper.
Right. Very cool.
I use an XFX for my main guitar playing. I use the latest and greatest technology, which is all digital, which is absolutely incredible as well. But I love both. I like the old stuff and the new stuff.
Right.
So,
right.
You know,
I like how you always say a valve and then tube. You know, it just shows
well, I say
shows
valves.
kind of.
I grew up saying valves. It's the British and Commonwealth name for them is valve, and the European name for them is valve. I only hear in America people call them tubes.
Yeah, so I do the opposite. I say tube, valve. You know, I've you hear the lookup go the other direction, right? Yeah. That's the Coriolis effect right there, by the way. You know, you say valve, I say tube.
That's the Coriolis effect. Yep. Dude, you know what I need to do, Bill? We need to make a sort of theme song for our show.
Well, one of us is a musician, so we should ask him.
Actually, both of us are.
Nah. But yeah, you should do it. So
yeah, one of these days.
Great talking with you again today. That was really cool, and I look forward to seeing that on the oscilloscope. I do. I'd love to see the sample and hold voltages and the control, you know, jumping them around and stuff. That'd be really cool. The control voltage.
I'll leave you with a tip. If any of you are guitarists out there and you're familiar with modern pedals, modern guitar pedals, really good, nice ones. There's a few out there that do this. They use the exact same techniques to control. So you can buy Jackson. There's a company in Texas, Jackson Audio. They make really, really nice guitar pedals. They're beautiful. A friend of mine uses them and he's an artist, so he has his own pedal named after him and everything. It's really cool. But they have MIDI control for their little guitar pedals. They're this big, but they have a MIDI jack on the back, and you can control them. You can set things with the knobs and use them like a normal pedal with analog controls. But then you can store the setting and store multiple settings and then
automate it. Yeah.
From a MIDI controller or a MIDI foot controller. Guess what? they're doing exactly this. They're using analog control voltages. They're using FETs and Opto isolators.
Right.
They're using they're probably using the equivalent of an Arduino, as the microcontroller for it, because there's so much support for doing MIDI and control stuff with Arduino. The libraries are just amazing, and it's so easy. And so, if you wanted to make your own stuff, you can totally.
You could do an I2C version of this. It'd be a cool project to do handfuls of analog, blocks, like companion blocks and whatnot, and yet make them all I2C controlled, and you could control it with an Arduino.
That's right.
That'd be a great homemade project.
The only challenge is if you want to reconstruct one of these older classic effects units, the parts can be really hard to get, because Toshiba, Hitachi, and NEC, the three main Japanese semiconductor companies that used to make all of these FETs. They made the low noise JFETs. They made the low noise transistor packages where you have super matched pairs and all this other stuff that was specialized for low noise, high fidelity, low distortion audio, analog audio stuff in the 80s. They all stopped making them. And so it's pretty tough to get some of the parts. You can still buy any 570 and 572 companders. I don't know if they're legit originals or if they're knockoffs. But I've found them on AliExpress. Maybe they're old stock that comes from other production runs in the past, but
I figured that you could cross-reference some of the FETs, but getting matched pairs and stuff, that you can't just cross-reference those and whatnot. So I assumed that there would be not as many FETs out in the world as there were back in our day, but that you probably could find one that would service a lot of do the job of the FETs we looked at.
There is one California company that's set up to replace them as the need has arisen for boutique audio and musical gear, called Linear Systems Corporation.
Right.
And Linear Systems replaced the 2SK, these Toshiba FET part numbers. 2SK 389. The 2SK 389 is a dual matched pair ultra low noise JFET. And they've replaced it with their LSK 389 from Linear Systems. But I think what they may have done is purchased some old semiconductor fab equipment and refurbished it to be able to continue with the same process that they used to use to make them the same. I don't know that for sure. That's my guess. But they make really nice parts. But I tell you what, they're expensive. An LSK 389 is going to be like $7-8 for one
for Op Amp. Matched pair, yeah. So.
And then they have the LSK 170, which is the replacement of the Toshiba 2SK 170. And 2SK 170 BLs you can still find, but the problem with JFETs is they were binned by IDSS.
Right.
And so for those who don't know FETs very well, they have this parameter, IDSS, and it basically means how much current do you have to push through the transistor to bias it into the middle of its linear region. I'm oversimplifying it, and that's not exactly correct, but that's the impact it has. If you have a higher IDSS rating, you have to bias the transistor on harder to get it into its linear operating region, and that causes it to warm up and deteriorate over time.
Which causes it to
they don't last as long, even though you can still buy them. They're the ones people didn't want to buy. You want JFETs with a very low IDSS rating for audio gain stages, because that means you're not going to have problems with your JFET wearing out, being hot all the time. So
all right. Excellent. Well, it was great talking with you again. I love the detail we went in there. I love the Opto isolators. That takes me back we could tell Opto Isolator stories, I'm sure, at some point.
Right.
So excellent. So any last words?
Yeah, make
well,
your own Opto isolators. Get some voltage dependent resistors and some LEDs and put them. We
used to be incandescent bulbs, and they used to do that because the incandescent bulb is an RMS converter. You know, it's
I actually had a tube. Yeah, that's right, because it smooths everything out. I had a tube amp, had one of them in it for the feedback. For a long time ago.
Right.
So yeah,
it was a way to have high voltage, do low voltage control, among other things. Yeah.
Yeah.
So excellent. All right, we'll see everybody here next week. Maybe we'll do a Commodore thing. We were talking about doing one every other week or whatnot. And then we're going to continue tearing into this old retro gear. Again, you got some old retro gear you want to unload, talk to us on Discord, whatever it's called. And, we'll get it on the bench for you. So, Ben, as always, great talking with you. I learned a lot, and good seeing everybody here this week. And we'll see everybody next week.
Yep. Thanks for coming.